The research that I was doing in this CERIC framework was on the topic of organic electronics, so specifically making and understanding devices made from organic compounds. And in this case I used perylene bicimide, a very small molecule that's widespread in paints and colors. And the advantage of this molecule is that it's very stable. I mean, if you consider a car paint, having it irradiated by sun over 40 years, keeping its color, this is something that's very, very resistant to external photo use. And that is actually the big advantage compared to other organic molecules that are not so stable. And in this case, I was able to, or actually we were able, as this was really a big collective effort, we were able to fabricate a fully organic based device, a humidity sensor, and we characterized it structurally, and by having this high resolution information we could identify the charge transfer points and really get a good structural comprehension in the theory, prove our theory of how charges transfer through this device and how the device works. The concept of this organic device is a nanofiber network. So this small die forms nanofibers, and these nanofibers then form a network. And it was known that within these fibers charges, so electrons can move and the fibers are conducting, but we asked the questions, how does one charge go from one fiber to the other fiber? So how does charge transport function on a larger macroscopic scale? And this is of course important, because if you want to improve such devices, if you want to really put them maybe even on the market, you have to find the points where you can optimize them, where you can enhance them, and of course how other systems that might be similar from a structural point of view work. I mean, understanding one system already tells you a lot about how similar systems might function, might work. To get a comprehensive picture of these devices, so to characterize them, starting from the atomic scale up, as I was saying, the macroscopic scale, we needed actually quite a series of characterization techniques. And in this case, the key information we got from X-ray scattering, so from synchrotron-based small angle and wide angle X-ray scattering. And from this experimental results, we were able to derive this highly resolved structural model. And once we had this idea of how this would look like, we needed imaging, so how this looks on the macroscopic scale. And this we obtained using scanning electron microscopy. So in fact, we required a bench of techniques, and the samples actually traveled to 5 different sites, different countries, and it was a big collective effort that at the end really, I think, turned out to be a nice result. We really provided one of the first consistent structural pictures and also theories on how these systems might work on from an electronic point of view, and I think we really set a good first step in this direction of general hydrogel usage. So CERIC really provided the infrastructure network that was necessary to do this research. As I was saying before, the samples traveled in up to 5 different countries, and we required a variety of different techniques. And CERIC really provided access to each of one of them. Especially the synchrotron-based techniques were really the key here. The other point that I think was really important was that we had all the experts, the different technique experts at hand. So if you had questions in preparing the samples and also evaluating the data, having the experts really contactable at hand and getting their know-how into this research was really a key part. And I'm very grateful for the people that were involved, and yeah, I think it turned out a very nice accomplishment.
Thank you very much, Dr. Burian, for this interview, and we wish you all the best for your future career. We look forward to meeting you soon at the CERIC. laboratories.
Thank you.